We are going to discuss now the second method that we can use to do the degrees of freedom analysis and the mass balance for reactive systems. I just want to draw your attention to a very important point, which is the difference between the two methods. So I made this diagram to make it clearer for you what we are doing, where it fits. So if we are looking at the systems that we deal with from the mass balance perspective, they can be either reactive systems or non-reactive systems. For the non-reactive systems, which are the physical systems, which are the systems that we covered before in the first part of this chapter, before we start discussing the reactions and all these details about the reactions. And for these systems, it's like the separators, like the mixers, like the extractors, like splitters. All these are non-reactive systems, meaning that there is mass balance that we can do on the system, but there is no reaction. So the number of moles of each species is constant. It just differs from the stream to another, but the total in equals the total out, and this is what we use to do here. So this is for the non-reactive systems. For the reactive systems, it's a different category of units, and we put it in a separate category because the calculations are different, and this is because we have a reaction, so the number of moles of each species will change, and the way we do the mass balance calculations would be different, and that's why we deal with it in a different way. And this affects, since we have different way of doing the calculations, this also affects the degrees of freedom analysis, and this is what we see in or we saw in the case of the atomic species balance, and we saw that the degrees of freedom is different, and the difference was in the way we calculate the number of equations, which is number of atomic species. And we will see in the extent of reaction is going to be in the number of variables, which is also because the way we do the calculations includes the extent of reactions. So the goal of these two methods is the same. So these two methods are two alternatives that we can use to do mass balance calculations on a reactive system. Mass balance calculations meaning that we have a system where there is a chemical reaction taking place, and we need to calculate some missing information. Either these are the flow rates of the feed, or the product, or the extent of reaction, or the conversion, or the yield. Any of these information are going to be calculated based on the mass balance calculations. So these are two different approaches for the same goal. The goal is the same in the two cases. And this has to be clear. There are differences in the way we do the calculations and the way we do the mass balance or the degrees of freedom analysis in the two methods, but the goal is the same. And this is what we will see in this video. We will solve the same example that we solved in the atomic balance method, and we will get the same results using a different method of calculations, which is the extent of reaction method. So I wanted to make this point clear, because in the class I found some students are confused and they feel that there is something that's not clear. So I hope this diagram that we see here clarifies things in a very simple way. So the extent of reaction method is different from the atomic balance method, is that we do the degrees of freedom analysis or the mass balance calculations on using the extent of reaction. And that's why we include reactions as variables. And if you remember, in this case, or it's going to be similar to the non-reactive systems from the point of including the variables, which are the number of variables in the streams, and we also include the independent reactions. And we will see this in details. In this case, we are doing the balance on the components that we have in the feed and in the product streams, and that's why we use the full equation, which is out equals N plus generation minus consumption, which is the same equation that we saw in 2 or 3 videos before. And we went through the similarities between these two equations, and that this is the out, this is in, this is the generation and consumption, and the stoichiometric coefficient is what tells us if it's generated, this species is generated or consumed. So the degrees of, for the degrees of freedom analysis, it's calculated the same way. The only difference is in calculating the number of variables, and in this case we include the reactions as variables, and this would be clear in the next example, or the next slide when we do the example. Number of variables is the number of components plus the number of independent reactions. Okay, so this is how we are going to do the calculations. So with the, I think things will be clear in this example here. So in this example we have the same ethane dehydrogenation to produce ethylene and hydrogen, and we have the reaction is C2H6 go to C2H4 plus hydrogen. And for the degrees of freedom analysis we have 1, 2, 3, 4 variables, and we have also one reaction here. So we have 4 plus 1. And I like to put it as 4 plus 1 to clarify for myself that this one is a reaction. It's not one of the components. The number of given variables is 1, which is the flow rate of the feed stream. The number of equations is equal to the number of components. So we have or number of species that we have in this system. So we have C2H6, C2H4, and hydrogen. So we have 3 balance equations that we can write. And for the additional relations, we have the same conversion relation that we had in the previous case, and then the degrees of freedom is 0. And this is the first good news here, is that we are getting the same result. Let's see, this is the example, and when we did the degrees of freedom analysis, it also was 0. We had different number of variables and we had different number of equations, but the output is the same. And this is something that we have to be 100% sure of, is that the output is always going to be the same. It's the same system. Whether you solve it using the atomic species method or the extent of reaction method, you are going to get the same result or the same output. So it doesn't matter what is the method that you are using, as long as you are doing it correctly, then you should get the same result. So this is for the degrees of freedom analysis. Again, if you compare this to any other non-reactive system units, these are the same way we are doing any non-reactive system. The number of given variables and the number of balance equations, the number of relations is the same. We only include here, this is the only difference, we only include here the number of reactions. So now let's write the equations that we have and start the solution. So if we write the balance equations, they are going to be very straightforward. We will have an equation for ethane, for ethylene, and for hydrogen. For ethane, number of moles out, which is number of moles of C2HC out, equals the number of moles of in, C2HC in, which is 100, plus the coefficient. The C2H6 is a reactant, so it's -1 times xi, which is the extent of reaction, so it's going to be 100 minus xi. The balance on C2H4, it's going to be the number of moles of C2H4 in, which is 0, plus +1, which is the coefficient of C2H4, it's a product, multiplied by xi, so it's xi. And for hydrogen, it is also 0, we have no hydrogen here, plus xi. These equations are not enough. If we go back to the degrees of freedom, we have already used these 3 equations, but everything is a function of the extent of reaction, so you have to find another information to calculate the extent of reaction, which is going to be the conversion. So if you go back to this the solution and we write the equation for conversion, it is the number of moles in minus out over in, so it's 100 minus number of moles of ethane in the product over 100 equals 0.6. So the number of moles of ethane in the product is 40 kilomoles per minute. If we substitute here, we can find that xi equals 60, and the same for the rest of the or we can substitute, we can substitute for C2H6 and hydrogen, and we can get the results. If you check the results that we got from the atomic balance calculations, it's exactly the same: 40 ethane, 60 hydrogen, and 60 ethylene, which is the same numbers, which are the same numbers that we have here. So it's again, it's not doing anything new. It's just another way of solving the problem using a different technique. In the next video we are going to have a bigger example, and we are going to solve it twice using the two methods, and we will compare the results and see that we are also getting the same results from both methods. So I'll see you then. Assalamu alaikum.